Alright, finally getting around to the chapter 6 homework review. It's been a crazy morning for me, so sorry this is out a little bit late. But let's go through some problems that we had the most difficulty with on this particular problem set, and hopefully this will be helpful to some of you that are still looking to take your exam, and if not, if you've already taken the exam, you can certainly use this to help you refresh some things before the final exam. Alright, so we're going to go over a lot of things related to reactions in solution. That's what chapter 6 is all about. So the first type of reaction we talked about is precipitation. So the first couple I'll go over deal with predicting products of precipitation reactions and whether a precipitate will form at all or not. So this first question, what precipitate, if any, forms when aqueous iron 2 nitrate is mixed with aqueous sodium bromide? So for these types of problems, we need to know the formulas of the reactants, and then we predict the formulas of the products by swapping cations and anions. And before I go into the specifics, I want to mention that for solubility rules, it's obviously annoying to have to learn all of them, and there's a decent amount of memorization you're going to have to do to really familiarize yourself with these rules. But always look for the obvious ones first. So there's the first rule is the one that supersedes all of them, which is if you have any of these cations in your compound. So these are going to be the group 1A cations, lithium, sodium, potassium, rubidium, cesium. Any of those cations plus this other one, NH4 plus ammonium. Or if you have the anions, which are going to be NO3 minus nitrate, ClO4 minus, which is perchlorate, or acetate, which can be written as C2H3O2 minus. If you have any of these cations or anions or both, these will always be soluble, and this rule supersedes all of the rest. Okay, so any compound that has one of these cations or one of these anions in it is going to be soluble. And then the other rule that's helpful to know is that if you have lead 2 plus, silver plus, and then the anions S2 minus sulfide, PO4 3 minus, which is phosphate, and the last one is going to be carbonate, CO3 2 minus. If you have one of these ions in your compound, these are going to be insoluble. And the only exceptions is if they're paired with one of those special one of those other cations or anions when paired with an always soluble okay, so lead with Pb2 plus with most things is going to be insoluble unless the anion that's with it is nitrate, perchlorate, or acetate. Sulfide S2 minus is going to be insoluble unless the cation that's with it is lithium, sodium, potassium, rubidium, and so on. So this first rule here, the always soluble one, supersedes all the rest, but then there's also a category of compounds that are pretty much always insoluble unless they're paired with one of those first ones. Okay, so with that out of the way, let's look at this specific problem. This will help us for both of the next two that we're doing. So if we have iron 2 nitrate, it's going to be FeNO3 and we mix that with sodium bromide, which is NaBr. The two products of this, without really worrying about balancing for now, are going to be iron 2 bromide, FeBr2, and then sodium nitrate, NaNO3. So we take the cation from the first compound and pair it with the anion from the second, so that gives us FeBr2. We take the anion from the first compound, which is nitrate, pair it with the cation from the second, which is sodium, sodium nitrate. So looking at the identities of these products, sodium nitrate is a very obvious one that's going to be soluble because anything with sodium in it is soluble, anything with nitrate in it is soluble. FeBr2 is a less obvious one. It's a halide, it has bromide in it, Br minus, and if we have the halide, specifically Cl minus, Br minus, or I minus, ionic compounds with these are usually soluble, and the only exceptions we have to remember are Pb2 plus and Ag plus. As I said, those two cations are always insoluble unless paired with one of the special anions. And then the other exceptions are going to be copper plus and Hg2 2 plus mercury plus 1, which exists as a dimer. So those four halides are insoluble. This is not one of the insoluble halides, so this will also be soluble. which means when we mix these two solutions together, we get two soluble products, which means we get no precipitation. So that would be the correct answer is E, no precipitate forms. Alright, the next question also deals with solubility. So we're once again mixing two aqueous solutions together. We want to know which one gives a precipitation reaction. So we have three situations here. Let's start with the first one. So the first one is sodium sulfide plus nickel 2 sulfate. So it's going to be Na2S plus nickel 2 and then paired with sulfate SO4 2 minus. So the two products of this reaction are going to be sodium sulfate, where we take the cation sodium and pair it with sulfate as an anion, and then nickel sulfide NiS. Alright, so which of these gives a precipitation reaction? If we look at the products of this has sodium in it, so it's definitely going to be soluble. All sodium salts are soluble. Nickel sulfide, like I said, sulfides are going to be insoluble unless they're paired primarily with the group 1 cations. This is going to be an insoluble compound, so this one will form a precipitate. So that one's one of our choices. Alright, sorry for that little break. And then going on to the rest of these choices here. Number 2, we're taking lead 2 nitrate, so that's going to be PbNO3 and we're combining that with potassium bromide KBr. So the two products of this, lead pairs with bromide to make PbBr2, and then potassium nitrate. And again, the obvious one, potassium nitrate is soluble because all compounds with potassium are soluble, all compounds with nitrate are soluble. PbBr2 is going to be an insoluble compound because lead 2 compounds tend to be insoluble unless they're paired with, like I said, nitrate, acetate, or perchlorate. So this one gives precipitation as well. And then finally, the last one, we have sodium iodide, which is NaI. We're mixing that with mercury 1 nitrate. So remember that mercury 1 is this weird cation that has 2 mercuries, each with a +1 charge, so there's a total of a +2. So the correct formula for mercury 2 nitrate is this here, 2 of each, because this whole thing exists as a polyatomic cation. Anyway, so the products of this are going to be sodium nitrate and the mercury 2 cation paired with iodide, so Hg2I2. Okay, so if we look at these combinations here, this one is obviously soluble, sodium nitrate, all of those are soluble, and then this one is one of our insoluble halides. So the insoluble halides are lead, silver, copper, mercury, so mercury is one of the insoluble halides. So all of these will give precipitation reactions. Okay, so that's the deal with precipitation. Alright, this next question here is a little bit of a tricky one, which also appears on the practice exam. So I guess if you did the practice exam and had trouble with this, you can look at this same exact question which is on there. And we want to know which of these would produce a 0.1 molar Ki solution. So there's a lot of numbers here, so we might think, well, we have to do so many calculations. But keep in mind the precise definition for molarity, which is capital M, is going to be moles of solute, which in this case is Ki, potassium iodide, and that's per liter of solution. So when you're preparing a solution with a certain molarity, you need to ensure that the volume of solution is correct. You don't just add that much water, you have to make sure that when you mix the water with the solute that you're dissolving, that that's the total volume. So some of these are worded incorrectly and we can just eliminate them. So in choice A, weigh out 1.66 grams of potassium iodide and add 100 milliliters of water. We're adding 100 milliliters of solvent, but that doesn't mean our solution volume is exactly 100. In practice, it's probably going to be very close, but this one can't be right because we're not preparing the solution correctly. We're just adding water, and we're not taking into account the total volume of solution. And then same thing for choice C. We're adding water from a graduated cylinder, but we're adding just a volume of water. For choice C, we will need to ensure that the volume of solution is 1 liter to be able to calculate the molarity accurately. And then finally, the rest of these all have, the wording is correct, but we're making a certain volume of solution. So now we have to do the math. So for choice B, for each of these we're going to take the mass and divide by the molar mass. So for choice B, the moles of Ki, we have 3.32 grams. Divided by 166. So this is going to be 0.0200 moles, and then that means the molarity is going to be 0.0200 moles, and then the volume of the solution in liters is going to be, sorry, we're going to divide that by the volume in liters. 50 milliliters of solution is 0.05 liters. And that gives us a 0.4 molar solution. Alright, so that's not the right molarity, so we can cross out B. If we do the same thing for D and E, this one is going to be 1 mole of Ki, 166 grams, the molar mass is 166, divided by 1 liter, so that's going to be a 1 molar solution. So that one we can do in our head. And the only one that's left then is choice E, which if we do the math is going to be 4.15 grams corresponds to 0.025 moles, and then the volume here of solution is 250 milliliters, which is 0.25 liters, which gives us 0.1 molar. So choice E is the only one where we have the correct ratio of moles to liters, and where we're preparing the solution correctly, where we're ensuring the volume of the solution is the correct number, not the volume of solvent that we had. Alright, so that one had a little bit of a trick to it, but hopefully it makes sense now, and that we'll see that one on the practical exam as well, so it's one we should definitely be familiar with. Alright, we had a couple other quantitative problems dealing with molarity. So the first one here is we want to prepare a solution with a sodium ion concentration of 0.256 moles per liter. So first we want to prepare a solution of sodium ions, which is Na+, and the concentration is 0.256 moles per liter, which we can also rewrite as, if we want, as 0.256 molar. And we want to know what mass of sodium sulfate is needed to prepare 1.73 liters of a solution with this concentration. So remember that when we dissolve an ionic compound in water, it splits up into its ions. So if we take sodium sulfate, which has a formula of Na2SO4, and we dissolve this in water, we get 2 Na plus and SO4 2 minus. So we're looking for a solution that has 0.256 molar sodium plus and a volume of 1.73 liters. So now we can set up a series of conversions where the key point here is that for every 1 mole of sodium sulfate that we dissolve, we're forming 2 moles of sodium ions. And that's the part that a lot of you will forget when doing these types of problems. So if we're looking for the grams of sodium sulfate that we're dissolving, we're making 1.73 liters of solution. We know the concentration of that solution is 0.256 moles of sodium plus per 1 liter of solution. So now we know how many moles of sodium plus we need, and then from there we know from this dissolution equation that for every 1 mole of sodium sulfate, that's going to give us 2 moles of sodium plus. So moles of sodium plus cancel out, and that gives us into moles of sodium sulfate. And then finally we use the molar mass of sodium sulfate, which wasn't given to us here. Let's figure out what that is real quick. Which is 142.05 grams of sodium sulfate in every 1 mole. So the last step is just going from moles back into grams, a very familiar conversion for us. And so when we multiply this out, if I did my math right, we get 31.4 grams. Alright, and this was a numerical question, so you could have had different numbers involved, but the series of steps is the same. We figure out how many moles of Na plus we have, we figure out how many moles of sodium sulfate that corresponds to, and then we convert that moles back into grams. This next question is very similar in concept. We want to know how many total moles of ions are released when the following sample dissolves completely in water. Strontium hydrogen carbonate, we have 7.42 times 10 to the 25th formula units. So what that means is that we're going to take, so strontium hydrogen carbonate, strontium 2 plus, and then hydrogen carbonate is going to be HCO3 minus. So the correct formula for this is going to be strontium HCO3 taken twice. Sorry, I got interrupted again. Okay, so we're trying to find what happens when we dissolve this many formula units of strontium hydrogen carbonate. We want to know how many total moles of ions are released. So we're looking for moles of ions, and we have 7.42 times 10 to the 25th formula units. So that's sort of the ionic analogy of a molecule. So we have that many units of strontium hydrogen carbonate. We can use Avogadro's number to figure out how many moles of strontium hydrogen carbonate we have. So if you have this many individual formula units, we can convert that into moles. And then finally, what we can look for is how many total ions there are. So remember that when we dissolve a compound in solution, it splits up into ions. This one's going to give us strontium 2 plus 2 hydrogen carbonates. So a total of 3 ions. There's 1 cation, 2 anions that are released when we dissolve this. So we're going to have 3 moles of ions for every 1 mole of strontium hydrogen carbonate that we dissolve. And so when we work out the math, we get in this case we get 369.6 moles of ions. Right, so quite a few, but remember we're starting with individual number of formula units. We use Avogadro's number to convert that into moles. But the key relationship that we saw here and on the last problem is when we dissolve an ionic compound in water, it splits up into its ions. So in solution, we're going to have, for every mole of strontium hydrogen carbonate, 1 mole of strontium 2 plus, 2 moles of hydrogen carbonate, a total of 3 moles of ions altogether. All right, the last couple that I want to go over deal with redox reactions. I guess the last 3 I want to go over. So the first one is asking us to identify oxidation and reduction reactions. So remember that in a redox reaction, also called oxidation reduction, you need to have oxidation numbers that change. Alright, so for precipitation reactions and for acid-base reactions, which are the other 2 major categories, we don't change any oxidation numbers, but for redox reactions we do. So the long way to do this problem, which I'll show you, is that we can take all these reactants and products in these 5 reactions, assign the oxidation numbers, and prove that they don't change between the reactants and the product side. So Br2 is an element by itself, so it's going to be 0, we have -1, and then on the product side we see that bromine becomes -1 and iodine becomes 0. So each of them is changing. Bromine is going from 0 to -1, iodine is going from -1 to 0, so this is a redox reaction. Copper plus has an oxidation number of +1, it's just the charge, and then on the product side we have +2 and 0. This is what's called a disproportionation reaction, where we have copper with 1 oxidation number on the reaction side, and it splits up into 2 different oxidation numbers as a product. But anyway, because the oxidation numbers are changing, it is a redox reaction. For this one here, which I think we've seen in one of the other assignments or in class, we have a +1 and -2 for potassium and chlorine, and then for potassium and oxygen, the chlorine in this case is going to be +5. On the product side, we have +1, -1, and then 0 for O2. So chlorine is changing from +5 to -1. Oxygen is changing from -2 to 0. We have changing oxidation numbers, so it's a redox reaction. So this one's a redox reaction. All three of these are. This one here, calcium is an element by itself, so it's 0. We have +1 and -2 for water. On the product side, we have a +2 for the ion, -2 and +1 for hydroxide, and then H2 is 0. Alright, so once again, we see hydrogen changing from +1 to 0, calcium changing from 0 to +2. This is a redox reaction. And then finally, if we look at the last one here, which should not be a redox reaction because all the rest are, but let's verify that. We have +1 and -1 for HCl, +1 for sodium, -2 for oxygen. That leaves a +4 for sulfur to balance the charges. For SO2, it's going to be -2 for oxygen, which is going to leave +4 for sulfur to balance the oxidation numbers to equal 0, +1 and -1, +1 and -2. So if we look at the oxidation numbers here, none of them are changing. Hydrogen is +1 all the way across on both the reactants and product side. Chlorine is -1. Sodium is +1 in both reactants and product side. Sulfur stays as +4. Oxygen stays as -2 everywhere it appears. So there's no changing oxidation numbers, so this is not a redox reaction. It may not be obvious what this is. This is actually just a fancy acid-base reaction. Not the conventional form that we're used to seeing, but it is an acid-base reaction. It's also clearly not precipitation, so that's really all that's left is acid-base. So this is the correct answer here. It's an acid-base reaction. Now that could take us some time because we had to assign all the oxidation numbers. I kind of breezed through it, but it might take you more time than I did to do it. One shortcut you can take for these problems is that if an element is involved, an element by itself, so that'd be a neutral element, it must be a redox reaction. That's a shortcut we can take for these. Because remember that elements are the only species where the oxidation number is 0. So if you have an element on one side of the reaction and it's changing to something else on the other side, its oxidation number has to change. It cannot change into something else that also has an oxidation number of 0. So if we look at this first reaction, we have an element, Br2, so this must be a redox reaction. Second reaction here, copper is formed as a product. It must be a redox reaction if it has an element involved. Third reaction here, O2 formed as a product. If there's any element by itself in the reaction, it must be redox. And then finally this one here, we have calcium as a reactant, and that's an element, a neutral element by itself, so that must be a redox reaction. So not all redox reactions will have elements in them, but if there's an element present, it must be a redox reaction, and we can quickly identify it without having to assign all the oxidation numbers all the way across. Because an element, no matter what, will change its oxidation number during the course of a reaction. Alright, so that was one that deals with assigning which one is an oxidation reduction reaction. Here we're talking about balancing a redox reaction and answering some questions about it. So the reaction is already balanced for us, which is nice. But now we want to see which one is oxidized, which one is the reducing agent, and the number of electrons that are transferred. So if we assign oxidation numbers first, copper is 0 as an element. For nitric acid, we have +1 for hydrogen, -2 for oxygen, and that leaves +5 for nitrogen. On the product side, this nitrogen now is +2 because it's paired with a -2 oxygen. Copper nitrate, we have an ionic compound, so you're going to have, it's a +2 copper salt because you have 2 nitrates. So the charge on the metal gives us the overall oxidation number, which is +2. Nitrate is still +5 and -2. And then we have our water, which is +1 and -2. So we notice that in this reaction, copper is going from 0 to +2. 0 for copper on the reactant side, +2 on the product side. And then nitrogen, we have some of our +5 from nitrate going to a +2 in NO. So oxidation numbers are changing, and the one that is increasing is going to be the one that is oxidized. So the element whose oxidation number is increasing is oxidized, so that's going to be copper. And then the reducing agent is going to be also the one that gets oxidized, but it's going to be the entire species that gets oxidized. So copper is the element that's oxidized, and that means whatever copper is with is going to be the reducing agent. Copper is by itself, so that means copper by itself is the reducing agent. Conversely, nitrogen is the element that's reduced, but the entire species that nitrogen is with, HNO3, is the oxidizing agent. Alright, but copper is the one that is oxidized, and it's going to be the reducing agent. So far choice A and D could work out, because the rest of them don't have the correct oxidizing agent and the correct first two choices. But now we need to find the number of electrons. If we look at the coefficients here, so each copper is losing 2 electrons each, but it has a coefficient of 3, so that's going to be a total of 6 electrons total. Alright, so even though each one is only changing by 2 electrons, there's a coefficient of 3, so in total, when balancing this equation, we have a total of 6 electrons. So that would be choice A. Okay, so remember that when we balance redox reactions, each element is changing by a certain amount. So nitrogen, again, is changing by 3 electrons for each nitrogen, but it has a coefficient of 2 in front of NO, so there's a total of 2 of those, which means it's going to be 6 electrons total. And that's what this question was asking for, was the total number of electrons that are being transferred during the oxidation reduction reaction. So the correct one for that is going to be choice A. Alright, and then finally the last redox problem is just balancing. We did okay on these for the most part, but this one we had a little bit of trouble with, so let's try to figure out why. Alright, so we're going to balance the redox reaction. Remember, the first thing we do is assign oxidation numbers. Let me rewrite this a little bit bigger so we can see it. Copper 2+, cerium 3+, and water to form cerium oxide, copper, and H+. Okay, so for this one we're going to have to balance the redox reaction, and so we assign oxidation numbers first, +2 for copper, +3 for cerium. They're ions by themselves. Water is always +1 and -2. If we go to the product side, if oxygen is -2, cerium has to be +4 to balance the charge. Copper by itself is an element, so it's 0. Hydrogen, H+ by itself is an ion, so it's +1. So those are the oxidation numbers which we need. Then we find the ones that are changing. Copper is going from +2 to 0. Cerium is going from +3 to +4. Now we have to think about how many electrons it is. So copper is changing its oxidation number by 2, so that's a 2-electron process. Cerium is changing its oxidation number by 1. It's going from +3 to +4. So that's going to be a 1-electron process. And now we need to make sure the number of electrons balance. So if this is a 2-electron change, we have to double that to make sure that they balance. So now we have 2 electrons for each of them. So we put a coefficient of 2 in front of each of those, such that now we have 2 + 3 is going to 2 + 4 is for a total of 2 electrons. We keep these coefficients as 1. If you want to write them in explicitly. And then the last thing to do is to balance everything else. So we have 4 oxygens here, 2 times 2. So we need to have 4 waters on the reactant side, and if we added 4 waters, that gives us 8 H+ on the product side to balance out hydrogen. So this one is looking for the sum of the stoichiometric coefficients on the right side. So the sum on the right side is going to be 2 for cerium oxide, 1 for copper, 8 for H+, a total of 11. So choice E is the correct one here. Alright, so like I said, there will be 2 questions on the exam dealing with balance and redox reactions, so definitely make sure that you cover those and are able to do that to the best of your ability. So that takes us to the end of this. If there's any other questions that I didn't go over, please feel free to contact me, and also ask me any other questions you have as you get ready for this upcoming exam.